13.6 cylinders and quadratic surfaces. So these are basically you somehow have to recognize which is which from given pictures and given equations, but then you don't really have to sketch. The sketching is not required, but highly recommended. Okay. So let's firstly review some curves in R2, the quadratic ones. Let's say we have x squared over a minus y equals 0. And now let's say a is positive. So in this case, this is actually a parabola, right? So basically, you plus both sides by y, you see, okay, this is a y equal to a positive constant times x squared. Right? So that's a parabola, and it's opening upwards because the coefficient in front is positive, so it's opening upwards. And basically, what does A do? So if you think about it, basically it's just like a thought. Okay. So if you make y equal to 1, and then these intersections have what? Have x squared equal to a. Right? So the larger a is, then this intersection will be further away. So that's the thought. But once again, in this section, the recognitions are, well, more important than sketching and something you probably know already. Now, what happens if you have an equation like this? You have x squared over x squared plus y squared over b squared equals 1. So this is actually an ellipse, right? So what's very important is that for the sketching, you also think about, I always think about those xy intercepts that this kind of equation can give you. So let's say if you make x equal to 0, you will have what? You have y equal to plus or minus b, right? So let's just assume that a, b are both positive. Okay. So they are the y intercepts. And then now if you make y equal to 0, you will have x intercept as a and negative. Okay. So you can imagine this is a highly symmetric curve, and it's actually the ellipse. So here you see the sketching is horrible, so but you get an idea. And in a sense, you can think about a and b as the shrinking parameters, right? If a equal to b, then you will have a circle with radius a, right? And then now, if you have a difference instead of a sum, then this is the very important curve, which is called a hyperbola. I'm just going to write it out. But then what's special here is that now, if you want to do the intercepts, this part you can make it 0, right? So if you have y equal to 0, then x equals to either a or negative a. But now you cannot really make x be 0. You can look at this. Okay. So if you make x equal to 0, you will have what? You have a negative quantity equals to 1. A negative squared quantity equals to 1. That's not even possible. Okay. So you have something like this. Whenever you fix a y value, then the x absolute value will just get larger and larger. But the smallest possible absolute value is a, right? So that's good. So you should be familiar with these, right? So those are just quadratic curves. Now, what about a surface? Now we move into 3D. So let's talk about the one that's relatively simple. So let's say z equals to x squared. Okay, so we mentioned that the surface in 3D, you always have one equation. Okay, so one equation defines your surface. If you have two, possibly it's like an intersection of two surfaces, which could be a surface needs to be one equation. Sometimes one equation doesn't even define you anything. Right, how do we sketch it? So basically, let's think about the easy case where we just have, let's say, y equal to 0. Okay. So if you look at this relationship, you only have the relationship between x and z, right? X, y. So let's say at the xy plane. So on xy plane, basically this the horizontal plane with no height, so that just tells you z is 0. What did I say? It should that's x z plane. It doesn't make sense to make z equal to 0 in this situation because it's not interesting. X z. X z. So y is 0. But it doesn't seem to, but it doesn't seem to affect anything. Right? So when you make y equal to 0 in this equation, x and z they're still following this equation with a quadratic expression. That tells you what y equal to 0 is this plane right here, and within this plane we just sketch the parabola opening upwards, like that. So this is exactly is equal to x squared, where you have y equal to 0. And if you put this plane, xz plane, on the right hand side, like this, then this is just z equal to x squared, which is the parabola. Looks a little bit fatter. And here the red one is just the way that you see it if you have this plane to be not exactly parallel to the monitor in front of you. Right, and now if you think about it, like we said, this equation has no y at all. So now y equal to 0, y equal to 1, y equal to 2. No matter what y value is, the shape of the parabola is always the same thing, right? In the xz plane. Okay. So for instance, if I pick, let me move it a little bit lower. So what's in red is the behavior of the surface on the xz plane. Right? But now let's say if I make y equal to 1, so this is a plane like this. So when y equals 1, what happens? So when y equals 1, we still, let me put in purple. We still have y equals to 1, and in terms of z is and x is z equal to x squared. So this is exactly the same shape. Okay. And the only thing different that here, the intersection between the purple parabola and your y-axis is that this is a 1. Earlier, we have just y equal to 0 right there. And you can imagine, okay, whatever y value that is, this parabola is always going to be the same shape. It's just shifted. You just shifted the y value. So this is exactly the kind of cylinder kind of a surface. Final result. So basically, on the horizontal direction, it's always a parabola opening upwards, okay, in terms of x and z. So let me just sketch the parabola right here. Okay, and basically you just shift to the left, right? So basically this, let's say this is y equal to 3. So the parabola is the black one, and I'm just gonna shift it all the way. It's gonna be the same, all the way to the left. And then I'll sketch the axes. So y-axis is the bottom one. X-axis, let's say, is right here. Right? And then z-axis is just going upwards. And then let me just sketch the red parabola, which is the exact same shape as the one on the left and right, right? So this is in red. That's exactly the red parabola that we have in the pictures above. Okay? So that's what we call the XZ trace. So we just call it the trace on the XZ plane, which is the intersection of the surface with the XZ plane. So now here we do have a sketching of the equal squared. So basically, whatever y value that you pick, that kind of plane is perpendicular to the y-axis. So that plane intersecting this surface that we have will always give you the same shape of a parabola, like this, or like this. Okay, so the shapes are exactly the same. Okay. I don't really need to include those, but just an idea. So it's good. Okay, pretty intuitive, right? For a cylindrical one. Okay, so this is called a parabolic cylinder. Okay, essentially it's a cylinder. And now, if you're just doing those perpendicular intersections, basically those if you pick y value to be a constant, you just have a parabola. So that's why it's called this name. So now, if you look at a similar question, let's say y squared plus z squared equals 1. So it's essentially the same idea. If you have y squared plus z squared equals 1, what does it tell you? Now, okay, this equation does not have anything about x, right? So this tells you, okay, if you make x equal to, let's say, 0, you will just have a circle, unit circle, right, in the yz plane. And now if you make x equal to 100, 200, the shape within that yz plane is always the same, right? So this is exactly a cylinder. So what I'm saying is, when you make x equal to 0, it's a circle. When you make x equal to, so that, yeah, the x direction is this direction, right? So basically here, just quickly give you a vision idea. So this is the circle like this, the same circle like this. So it just goes all the way from the front to the back. It's just quick sketching, but we don't really want to mess the previous figure up. So I'm just drawing it here. So it's the same circle up front, and it will just go all the way to the back. Same shape. And let me make the dashed lines for the transparency. And here I'm gonna say what happens when x is 0. So the axis So this is the axis, x-axis. And okay, going to the right, that's the y direction. Going vertically out, that's the z direction. So this red one is where we have y squared plus z squared equals 1, and the same time x is 0. So this is the yz trace. So this is exactly the curve that you will get when you have x equals 0. Or in other words, you're on the yz axis. And now basically you see, okay, for whatever x that you fix, that's cutting through, there will be just a circle. Okay. The equation is exactly the same equation. Was it good? Okay, so once again, just quickly mention that these the sketching for this entire section is not required, but you do need to know. Okay, let's say I'm giving you this equation, I'm giving you several figures. You need to be able to tell which figure is this associating to this equation. Okay. All right. So these are cylindrical. These are cylindrical shapes. So this is just a cylinder. Cylinder. So the previous one for parabolic cylinder. So this is you can say this is a circular cylinder. Right. So this is a really standard cylinder. So now let's look at quadratic surfaces. So we do see that the traces are important, right? So in the previous example, we see those if you fix x equal to 0 in the figure right in front of us, or in the previous situation, it was what it was y equal to 0, y equal to 1, right? So those are traces that are highly critical. Let's have a look at some more examples that are a little bit more involved. So let's say we have a surface, and we're going to put in the equation on the right. X squared plus y squared over 4 plus z squared over 9 equals to 1. Okay, so if you look at the formula, if you only have this part equals 1, that's actually an ellipse, right? But here it looks a little bit more general in the sense that we are plotting another square term in terms of z. Okay. So now if you think about it, if you make, let's say if you make z equal to 0, you will have an ellipse in terms of the xy plane. Okay. Now if you instead, let's say make x equal to 0, you will have what? You have in the yz plane that you have another ellipse. Okay. And this is very interesting. So what does it tell you? It tells you, just like I mentioned, for the z direction, if you make z equal to 0, you will have an ellipse, which is a horizontal one. Okay. But now if you make, let's say, if you make x equal to 0, you will have a vertical. So to simply describe what I'm trying to sketch, that's exactly you can say a football shape. So here I'm just gonna illustrate what I've done now. So this one in black, this is the parabola, well, excuse me, the ellipsoid that you get if you have z equal to 0. X squared plus y squared over 4 is now 1, right? So that's as an ellipse. This is the xy trace. Now, what's in red is the one that you get if you make x equal to 0. And when x is 0, you have y squared over 4 plus z squared over 9 equal to 1. Okay. the y-z trace. And of course, if you make what? If you make y equal to 0, just give you the idea of the y direction. Okay? So if you have the y direction to be 0, then you have another ellipse, which is like what, like right here. So of course, the transparency looks kind of ugly here, but this is where you have y equal to 0, and then x squared plus z squared over 9 is 1. Okay. So this is the XZ trace. Okay, so let's fill out the axes. Okay, so basically that's the center. This x direction going towards the right, that's the y direction. Going upwards, that's the z direction. And then those intercepts will be identified by those values that you can solve, right? So basically, the y value here, the largest is a 2, okay? Because here, x is between -1 and 1, and y is between -2 and 2. Okay? So this intercept on the x-axis is 1. Okay. This point, okay. This point, that's 2. This solid point here is 1. And now for the red one, we have this point, that's what? That's z equal to 3, right? Okay. So this is what's called an ellipsoid. So basically, this is say, okay, for whatever direction that you pick, the intersection is always an ellipse. Okay, so a very special shape. Looks like a football. So now these are 3 traces we have drawn, right? So what happens? Let's say if you make, let's say y equal to -1. So let's just sketch one more. So basically, we're making x equal to 0, y equal to 0, z equal to 0. Right? So what happens if you have z y equal to say -1? So if y is -1, then let's see. If y is -1, then this is what? This is 1 squared over 4. Okay, so which is a constant that you can subtract on both sides of the equation. So this essentially becomes. X squared plus y, x squared plus z squared over 9. On the right hand side, this is 1 minus 1/4. So that's you see, that's just comparing with this one. The constant right here is smaller, right? So the xz trace has a right hand side of 1. But now when we have y equal to -1, the right hand side is smaller. That tells you what? It tells you the shape is exact similar shape, but the ellipse is just smaller. Okay? Which is expected, right? Because we're just saying, okay, I'm just not gonna cut a smaller ellipse a little bit to the left. So that's okay. But similar shape, right? And for this corner, that's this is the end, which is -2. Okay? So y equals to -1 is exactly in the middle. It's just a smaller ellipse. Okay. And you can imagine if you, let's say, if you make x equal to 0.5, it's something really parallel to the red ellipse, right? If you make, let's say, z equal to 2, it will be an ellipse that's somehow horizontal, and it's similar shape as the black one, right? Good. Okay. So now you see those traces are very important. Okay, so they're definitely going to help you if you are doing the sketching. So as a quick remark, well, I don't really So this is actually a comment. So we don't really write the remark at the beginning. So to sketch surfaces in R3, make use of traces. The curves of intersections. With planes. Especially those axis planes. Okay. So XY plane, YZ plane, XZ plane. So now let's look at another example where we have Z now equals to Y squared minus X squared. So now, basically, if you think about it, when we are doing traces, right, we're just saying we will fix Z as a constant or X as a constant or Y as a constant, right? But here, if you think about it, it's really interesting. So if you make, let's say, X equal to a constant, then you just have a problem in terms of Y and Z, right, opening upwards. But now, if you make Y as a constant, you have a parabola opening downwards in the XZ space. Okay. So that's actually pretty interesting. And now, if you think about making Z a constant, you see this is a hyperbola. Okay. So that's actually pretty interesting. So let's try to sketch. Let me firstly get the axes. So we just said, okay, if you make X as a constant, you will have parabola, right? But let's say X is 0, so we are on the YZ trace. So it's exactly Z equals to Y squared. It's a parabola opening upwards. Okay, in the YZ plane. Okay, so to simply write it down, so this is X equals 0. So this is Z equal to Y squared. Okay, right here. And now, if you think about making Y equal to 0, this is Z equal to negative X squared, right? But Y equals to 0, that's in the XZ plane. Okay, so it's somehow in on the side that's on the left. So we want to make it a little bit not as fat as the one that we have, and it's opening downwards. And for transparency, I'm gonna do a dash lines right here. Okay, so this is where we have Y equal to 0, and we have Z equal to negative X squared. Okay. A parabola opening downwards within the XZ plane. Okay. So now, so here we do see this kind of two parabolas just going on different directions, right? So now we're gonna do some different traces. So let's say we just mentioned when Z is a constant, right? It will give you hyperbolas, right? So when it's high above, let's say when Z is positive, okay? When Z is positive, let's say 10, right? So this is Y squared minus X squared equals to 10, or Y squared over 10 minus X squared over 10 is 1. So that's a hyperbola opening along the Y direction. Okay. So to give you an idea, I'm going to put it in red. Opening on the right along the Y direction is something like I want to do that. Something like this. So it's a hyperbola opening along the Y direction, where you fix Z as a positive constant. So let me just put this is Z equals to some constant A that's positive. Okay, so does that make sense? when z is positive, your y value must be positive and x could be 0. So that's what happens. All right. Now, what happens if you make z negative? If you make z negative, let's say -10, okay, then you see, okay, and you can flip both sides, the sign, then this is a tan equals to x squared minus y squared, right? So it tells you that that's a hyperbola opening along the x direction, which is exactly opposite as the hyperbola that we have established, namely right here. And put it in the lower. And it will be on the negative side as well, but I'm gonna just sketch it like this. So basically, it's intersecting this point and that point. Okay, so that's where you have z equal to some constant. Let's say a is positive, so we have z equal to negative a. So that's negative. So we're almost done. So let me fill out several other curves to establish what's going on. So this whole thing here is actually entire piece. This is the entire piece. And if you look at the back, I'm just gonna connect this side, and I'm gonna connect that side. And this is solid. Let me erase y here. I'm gonna put it right here. So you get an idea of the shape of this surface. Okay? It looks like a horse setup. Okay? So this is called hyperbolic paraboloid. Because basically, when you think about it, if you fix x, it's gonna be a parabola. If you fix y, it's gonna be a parabola. So along two directions, you have paraboloids. They have parabolas. But if you fix z, it's gonna give you hyperbola. Okay, that's why it's hyperbolic in the front. And also there's another trace that I can quickly establish. So basically, the things in red, if you think about it, okay? So the curves in red are hyperbolas that you get when you make z equal to a or negative a, right? What happens if you make z equal to 0? Think about this. So when you make z equal to 0, I'm gonna put it right here. Okay. So when you make it z equal to 0, you have what? You have 0 equals to y squared minus x squared. And you do know that the right hand side can be factored. Okay. So 0 equals to y squared minus x squared. And that's exactly 2 lines, right? This is exactly y minus x equal times y plus x. So that's just the line y equal to x and the line y equal to negative x. Okay. So it's kind of like a degenerated hyperbola. And exactly that's within the xy plane. So you can just let me just sketch it in red again. So this is a line. This is y equal to x, right? If you imagine that. And I'm gonna extend it to the back. And then for y equal to negative x, that's exactly perpendicular. That's in the front. So solid. And the back is dashed. Okay. So that's that's the xy trace. Okay. So we didn't establish the xy trace at the beginning, but now we can do it here. And that's this. That's this. So that's why I'm saying we don't really require you guys to sketch because it's definitely not so simple. But at least when you are seeing this, you somehow need to relate to the equation right at the top. Okay. Okay, let's look at some more. So definitely, the more you see, the better. Okay. So the next one is really similar. So now this is z. So we had z equal to x squared minus y squared, right? What happens is a plus. So if it's z equals to x squared plus y squared, if you follow the similar logic, so you make this as a constant, x is a constant, you have the parabola opening upwards. If you instead make y to a constant, so that's parabola in terms of x and z opening upwards. So fortunately, they have parabolas opening upwards. And now if you make z a constant, you have what? You have a circle. Okay. And in this situation, you don't really have z the option to be negative, right? So earlier in the picture right above, we have z equal to a, z equal to negative a. Those are hyperbolas opening along different directions. Okay? But here, c looks like this z can only be positive. So that's much simpler. So that's the axes x, y, z. So basically, what I'm saying here is that I'm putting in red. So when you have x equal to 0, right? That's z equal to y squared. That's actually this one. So x is 0. We're in the yz we're in the yz plane right here, right? And then when we are having y equal to 0, that's z equal to x squared. That's actually within the xz plane. But now it's the front, and this is the front, the piece on the front and the piece at the back. Okay, so we have two parabolas. And now what happens if you have z equal to some a positive constant, let's say 1, right? If you have z equal to 1, what do you have? You have a circle, x squared plus y squared equal to 1, right? Right here, circle. So there are a few intersections. Let's say this is the intersection, this is the opposite intersection, this is the intersection, this is the intersection, right? So now you see, okay, the purple one definitely is a circle. Well, although it may look, it may look like a circle, but you just try to imagine that it's a circle. Okay? So when z equals to 1, you have x squared plus y squared equals 1, right? A circle. So this is called a paraboloid. And paraboloid. Well, but it is a elliptic paraboloid. So it's just a standard paraboloid. So basically, here, if you fix x to be constant, it's a parabola. If you fix y as a constant, it's a parabola. So that's why it's called a paraboloid. But now, if you have, let's say, z equal to really similar, right? Z equal to, let's say, x squared plus 4y squared. So that tells you if you fix c as a constant, you will get an ellipse, right? So here, if you fix z as a constant on the left-hand side, that's just a circle. And now this is a little bit more general, so that's ellipse. Okay? So that's why it's called elliptic paraboloid. Yeah, so to make the figure look a little bit nicer, let me draw a top as well. So to get a larger circle for the top. So that's that was good. So you guys will be able to see more figures as you work on the MyLab questions. And this top. Okay. More sketching. So actually, let me see. We have two more figures to go. So here, let's do x squared over 4 plus y squared over 1, so y squared minus z squared over 4 equals 1. Okay. So if you're looking at this one, So basically, what do you see? So if you have, let's say, x equal to 0, this is ellipse. If you have y equal to 0, this is another ellipse. Oh, what did I say? If you have x equal to 0, you have a hyperbola. If you have y equal to 0, you have another hyperbola. Okay. And z could be 0, but x and y could not be 0 on this in this situation. But then if you make z equal to 0, you have an ellipse, right? So let's do those traces first. X, Y, Z. So basically, X, Y trace is ellipse. Okay. So Z equal to 0, right? Now within the same picture, let's do like we mentioned. If you make y equal to 0, it's a hyperbola. And if you make x equal to 0, that's another hyperbola, but the shape is well, the shape is different, but the idea is the same. Okay? So when y is 0, what do we have? We have something like this. Right? Going through this one and this one. Right? So that's the XZ trace. So yeah, let me quickly get the idea for the traces for you. So when you have y equal to 0, I mean you are in the XZ plane. That's actually the hyperbolas right here. Okay. So now you can see what's going on. So basically, when you fix z as a constant, the ellipse just gets larger. Okay. So basically, if we want to sketch the figure, well, of course, which is not required, but basically you just want to start with the traces. Okay. Here, what we see is that the parts that are positive on the left-hand side, and there's negative part on the right-hand side. Excuse me, on the left-hand side. So if you make, let's say, x equal to 0, you will get a hyperbola. If you make y equal to 0, you'll get another hyperbola. If you make z equal to 0, you will have an ellipse. So that's why we call it elliptic hyperboloid. So basically, along two directions, you will have hyperbolas kind of traces. Okay, and then along one, you have a kind of ellipse that's in purple, right? So the ellipse is in purple, and you have hyperbolas in black and red, and they do intersect, right? And then, so you can summarize. So if you make, let's say, y equal to some positive number, then you have a larger ellipse, right? So if you make y equal to, okay, if you make z equal to some constant, let's say 100, right? Then you're gonna have a really high up ellipse, which is very large. Okay? That's the idea here. And now we're going to look at another, this is the last example. So basically, negative x squared plus y squared over 4 minus z squared over 2 equals 1. So now in this case, we have something different. We have one term that's positive on the left-hand side, but there are two negatives, right? Let's see how it goes. Basically, we start with the traces. Quickly sketch. X, Y, Z. So let's say we start with making let's say x equals 0 now. Okay. So when x equals 0, what do we have? We have the YZ trace. Basically, is in the YZ plane. So let me make it red. So when z equal to when x is 0, we have what? We have basically y squared over 4 minus z squared over 2 is 1. So this is a hyperbola that's opening along the y direction, right? So y is always greater than or equal to 2 in terms of the actual value, right? Z could be 0. This. And of course, this is the negative side. YZ plane. And that's a 2. That's a 2. Negative 2. Right here. And now, so this is the, yeah, let's put it in red. This is red. So YZ trace. And now, if we make y equal to 0, oh, it's somehow something that's not making sense, because if you just make y equal to 0, what do we have? We have negative x squared minus e squared over 2. So left hand side looks to be non-positive, right? But the right hand side is 1. So this doesn't even make sense. So basically, when you think about it, so this is if you have, say, negative 100 or something on the right hand side, then okay, you have an ellipse. But this unfortunately is not legal. This is not an equal ellipse. So what that means is that there's no chance that you will have y equal to 0. So that means within the xz plane, within this plane, there's nothing as a trace at all, right? And we can move on to let's say z equal to 0. Z equal to 0. Let me use the black color. So z is 0. That tells you negative x squared plus y squared over 4 is 1. So this tells you this is another hyperbola. So this is the plane where z is 0. So that's the xy plane, right? So xy trace. And we notice that, okay, the y-intercept is again positive negative 2, right? When you have x equals 0. That's this code. And make it a bit better looking. Okay. So that's my xy trace. So that's my yz trace. That's my xy trace. Right, in the horizontal plane. And now, somehow we can say, definitely we know, okay, along 2 directions we have hyperbolas. Okay, but then along the direction where you make y equal to a constant. So of course, when y is 0, there's nothing, right? But what happens if we have y equal to 1, y equal to 2, y equal to 3? So let's see. So basically, if you look at the picture here, so these 2 red dots, let me make it a little bit larger. So this is a red dot of y equal to 2 or negative 2, right? So basically, what here is that y cannot have a smaller absolute value. Otherwise, you will really not get you will not really get anything reasonable. So let's just rewrite this equation that we start with. So basically, we have rewrite. So we're trying to make y equal to a constant, and we want to get a trace, right? So that's minus both sides by y squared over 4, and then we just flip the signs on both sides. So we'll get x squared plus d squared over 2 equals to y squared over 4 minus 1, right? And here we're just making this constant. We're just making the right hand side constant. So basically, this is saying, okay, when y is 2, the right hand side is 0. So that's exactly the red dots, right? But when, so this thing equals, let's say, when y is 2, is a 0. When y is, let's say, 3, the right hand side is what? When y is 3, we have 9 over 4 minus 1. That's 5 over 4. Okay, so that's a legal ellipse, right? Well, we have y equal to, let's say, 4. What do we have? We have right hand side equal to 3, right? And we see the right hand side gets larger. Okay, so definitely it's going to give us something when y is getting larger and larger, right? So at first we have the red dot, which is at y equal to 2. But then when y is 3, we have an ellipse. it doesn't look really like an ellipse, but let's make it better. Okay. So that's our trace where y equals to, let's say 3, and here we have x squared plus z squared over 2 equals to 5 over 4, right? And it could get larger. So this is where we have 3, right? And then when y is 4, it's somewhere like here. So it's even larger. Even larger ellipse. Three. Okay. And you can imagine that if you make y equal to -3, it's going to be the same ellipse on the left hand side here. And if you make y equal to -4, it will be even larger. Right? Right. So that's a kind of a sketching. So if you want to make it even better looking, we're gonna sketch it. I don't really have that much space. Yeah. Any questions so far about sketching? Any questions so far? Should be good, right? So we have done this quite a few times. So basically, the idea here is that this is kind of a hyperbolic shapes on this piece, right? And on this piece. So it's going to be called elliptic hyperboloid of two pieces. Okay. We have two pieces here. So, and they are symmetric in terms of the vertical plane. So quickly sketch it. It's symmetric. There's something like this. Okay. We have an ellipse. We have another ellipse. And it's symmetric on the left hand side as well. If you want to quickly sketch it and make it look nice, this X one. So this is the elliptic hyperboloid of two sheets. It has two pieces. So once again, in this section, you don't really have you are not really required to sketch these in your exam or written homework, but you need to recognize when you're given like let's say 4 equations and 4 figures, you need to somehow be able to match with each of those, right? So that's pretty much it about this section. Any questions so far? Right. So if this is good, let me quickly mention another example that's for you to think about. Okay. So what we have done for the previous 2 examples is that okay. So in the one right here, we have 2 positives and the negative, and the 1 on the right hand side, a constant on the right hand side. Here we do this, where we have 2 negatives and 1 positive on the left hand side, and the right hand side is 1. So what happens? Think about this. Okay, what happens if I just make this 0? So that will give you eventually a code. Okay, so yeah, I'm just gonna copy this, and I'm gonna make this a question that you can think about. Okay, so try to utilize some kind of a website to get a professional illustration, or think about it yourself how you're going to sketch it. Okay. So we have done something similar to this when we are doing the whole saddle kind of shape. Okay. So basically, if you have a 0, right, if you have a 0 right here, then if you make x equals 0, then this is something, this is square minus another complete square that you can factor and you get something interesting. That's basically what I'm giving you here.